Ethereum is often described as digital money, but that is only one small part of it. The bigger idea is a public computer that no single company owns. People can use it to send assets, create financial tools, issue collectibles, run games, or build applications whose core rules are enforced by code. That sounds powerful, but it creates an immediate question. If thousands of independent computers are running the same programs, who pays for the work? Who decides which results are valid? And what happens when the code goes wrong? That is where ETH, smart contracts, gas, and validators fit together. First, the names. Ethereum is the network and the software platform. Ether is its native asset, usually identified by the ticker ETH. People often use Ethereum and ETH interchangeably, but they are not the same thing. Ethereum is the system. ETH is the asset used inside that system. Ethereum launched in July 2015 with a broader goal than simply recording payments. Bitcoin had shown that people could maintain a shared digital ledger without putting one bank or company in charge. Ethereum extended that idea. Instead of only tracking who owns digital money, it can also track the state of programmable applications. Imagine a shared vending machine on the internet. The machine has rules. Insert the correct asset, select an option, and the machine performs a specific action. No employee needs to approve each request. On Ethereum, that machine is a smart contract. A smart contract is a program stored at an Ethereum address. It can hold assets, remember data, receive transactions, and execute predefined functions. One contract might exchange 2 tokens. Another might issue a digital membership pass. Another could require 3 out of 5 people to approve a payment before funds move. The word contract can be misleading. Smart contracts are not automatically legal agreements, and they are not intelligent. They are programs. They follow their code, including any mistakes in that code. This programmability is the main reason ETH is used beyond ordinary payments. Ethereum can support tokens, stablecoins, decentralized exchanges, lending protocols, NFTs, prediction markets, identity tools, and many other systems. The website you see is usually just the front end. The important rules and balances may be recorded by smart contracts on-chain. If you enjoy explanations that make crypto mechanisms understandable without the hype, subscribe. Now, let's follow an actual Ethereum transaction from beginning to end. Suppose you want to exchange one token for another using a decentralized exchange. You open the application's website and connect your wallet. Connecting normally lets the site see your public address. It should not reveal your private key, and it does not automatically give the application permission to move everything you own. You choose the tokens and enter an amount. The website prepares a transaction calling a function in the exchange's smart contract. Your wallet then shows a request containing details such as the contract address, the action, and an estimated network fee. When you approve, the wallet uses your private key to create a digital signature. The private key should remain inside the wallet. What leaves is the signed instruction, which proves that the account controlling that key authorized the transaction. The transaction is broadcast to Ethereum. A validator may include it in a proposed block, while other participants check that the block follows the rules. Ethereum nodes execute the transaction using the Ethereum Virtual Machine, or EVM. Every correctly functioning node should reach the same result from the same starting state and the same transaction. The exchange contract checks its conditions. Do you have enough tokens? Has the contract been authorized to use them? Is the exchange rate still within the limit you accepted? If everything passes, the contract updates the relevant token balances. The blockchain now records the new state. The tokens did not physically travel through your wallet or across the internet. Ethereum's shared records change to show that one address controls fewer units of one token and more units of another. Several things can still fail. The market price might move beyond your chosen tolerance. The contract could reject the transaction. You may have approved the wrong token or interacted with a malicious website. The contract itself might contain a vulnerability. And even when execution fails, you can still pay for the computing work already performed. That computing cost is measured using gas. Gas is not a separate token. It is a unit for measuring how much computational effort an Ethereum operation requires. A basic ETH transfer uses relatively little gas. A token exchange may call several contracts, read stored data, perform calculations, and update multiple balances, so it usually consumes more. Your final network fee depends on the gas used and the price paid per unit of gas. That price is commonly displayed in gwei, which is a very small denomination of ETH. All Ethereum gas fees are ultimately paid in ETH. A transaction fee generally includes a base fee set by the protocol, and a priority fee that rewards the validator proposing the block. The base fee is burned, meaning that ETH is removed from circulation. The priority fee goes to the block proposer. Wallets normally estimate these values, so users do not have to calculate them manually. You also specify a gas limit, meaning the maximum amount of gas the transaction is allowed to consume. If the operation needs less than the limit, the unused portion is not charged, as if it had been consumed. But if execution runs out of gas, the state changes are reverted, while the fee for the work performed is still paid. Why make users pay for computation at all? Because Ethereum is shared infrastructure. Without a cost, someone could flood the network with pointless requests, or create programs that run forever. Gas prices each operation, limits resource use, and forces applications to compete for finite block space. This also explains why fees can rise. When many people want to use Ethereum at once, demand for block space increases. Users may offer higher fees for faster inclusion. Ethereum is not promising unlimited computation. It is creating a market for access to a limited shared resource. So who maintains this system? Ethereum uses proof of stake. Validators commit ETH to the protocol and run software that helps propose blocks and vote on which block should become part of the accepted chain. Running a solo validator requires meeting the protocol's staking requirements and maintaining connected hardware. People can also participate through pools or services, although those introduce additional smart contract, custody, or operator risks. Validators can earn ETH for performing their duties correctly. They can lose rewards for being offline, and serious rule violations can lead to penalties known as slashing. The stake acts as economic collateral. Instead of proving commitment by spending electricity on mining, validators put ETH at risk. Validators are not free to rewrite balances or approve invalid transactions. Other nodes independently verify the rules. A validator proposing a block that creates ETH from nowhere or spends someone else's funds would have that invalid block rejected. This design separates Ethereum from Bitcoin in an important way. Bitcoin is primarily designed as a decentralized monetary network, with a deliberately more limited scripting system. Ethereum is designed as a general-purpose platform, where applications can maintain complex state and interact with one another. Ethereum also differs from networks such as Solana in how it approaches scale. Solana aims to process more activity directly through its base network, using a different architecture. Ethereum increasingly pushes frequent, lower-cost activity onto Layer 2 networks, which execute transactions separately and then use Ethereum for data or settlement. Layer 2 networks can make Ethereum-based applications cheaper and faster, but they add another layer of assumptions. A user must know which network their assets are on, how withdrawals work, whether a bridge is involved, and what security controls the Layer 2 still relies upon. Seeing an Ethereum-style address does not guarantee that funds are on Ethereum mainnet. Ethereum has other trade-offs too. Smart contracts can contain bugs, and public code is not automatically safe code. Transactions are generally irreversible. A convincing phishing page can trick someone into signing a harmful approval. Private keys can be lost. Activity is public by default, so Ethereum should not be mistaken for a private payment system. Applications can also depend on off-chain pieces. A smart contract cannot directly look up the weather, a stock price, or the result of a football game. It needs an oracle to bring that information on-chain. If the oracle is wrong or manipulated, the contract can execute perfectly and still produce a bad outcome. Even decentralized applications may use centrally hosted websites, development teams, administrator keys, or upgrade controls. The blockchain can make specific rules verifiable, but it does not magically remove every middleman or every form of trust. So, what is Ethereum in one sentence? It is a public blockchain that combines digital assets with programmable accounts, allowing people to run shared applications without one company controlling the underlying ledger. ETH pays for computation, helps secure the network through staking, and can move through the applications built on top. Smart contracts define the rules. Gas measures the work. Validators help the network agree on the result. That combination is why Ethereum remains such an important part of the crypto conversation. It turned the blockchain from a payment ledger into a platform where money and software can interact. The same flexibility creates useful tools, but it also creates complexity, fees, and new ways to make irreversible mistakes. If there is an Ethereum concept you still want unpacked, leave your question in the comments and suggest what we should explain next.